With the highly anticipated release of version 4.87, Docker Desktop has undergone its most significant architectural upgrade to date. Docker is moving away from its historical reliance on third-party virtualization technologies, like Hyper-V on Windows or VirtualBox on macOS. In their place, Docker has integrated a proprietary layer named Docker Virtual Machine Manager, or Docker VMM. For thousands of developers working on Windows and macOS, this change targets the persistent, often invisible performance bottlenecks found in local development environments. These friction points typically appear as sluggish file I/O operations, heavy system memory footprints, and slow container startup times. To address this, Docker is now vertically integrating the entire runtime environment, controlling the infrastructure beneath the containers. Instead of patching together general-purpose third-party tools, Docker is implementing an environment built strictly to optimize container workloads. By taking complete control of the virtualization layer, Docker manages the hardware-to-container pipeline directly, changing its role within the localized development stack. Running Linux containers on a Windows or Mac OS machine requires a virtualization layer to provide the necessary Linux kernel. Historically, this was achieved by leaning on general-purpose hypervisors. In the legacy stack, a rigid hypervisor block sits between the host OS and container. Built for full virtual machines, it requires static resources, locking away host RAM even when idle. File operations must also navigate multiple intermediary layers to reach the host file system. These routing requirements add layers of latency to every local development task. This complex initialization sequence is the primary cause of the slow startup times often associated with local container environments. While containers are intended to be lightweight, the legacy hypervisor stack imposes a heavy infrastructure that limits their agility. The friction isn't found in the container standard itself, but in the virtualization layer required to run it. This illustrates the efficiency gap created when using general-purpose virtualization for highly specialized, singular workloads. Using full virtual machines to support local containers creates an architectural mismatch that results in consistent resource bloat. Docker VMM provides a proprietary path that bypasses the legacy hypervisor entirely. The design focuses on a lightweight virtualization layer tailored exclusively for container workloads. In this new architectural stack, the bloated virtual machine block is removed. By removing the features required for full OS simulation, VMM reduces the volume of code that must be executed to support the container. This architectural thinning results in significantly lower virtualization overhead.
Lower overhead translates directly into a faster initialization process when starting a new instance. Code execution is faster, CPU boot speccing is reduced, and containers reach readiness immediately. For a developer, a frictionless startup sequence increases the speed of every iteration during a testing cycle. Rapid iteration cycles replace the weight-heavy workflows required by previous versions of the software. Eliminating the simulation of entire machines allows containers to function with the speed they were originally designed for. Beyond startup, application responsiveness is dictated by file I/O and memory management. High-performance file I/O is vital for applications that frequently read and write data to the host drive during development. Docker VMM establishes a direct pathway for data access between the container and the host file system. By removing legacy routing, VMM reduces latency and improves overall application responsiveness. This update also addresses the rigid memory constraints common on standard development hardware. Instead of static allocation, Docker VMM uses intelligent memory management. Containers now consume only the RAM they actively need, with footprints expanding and contracting based on the workload. This dynamic scaling prevents resource wastage when background containers are idle. This allows for the local operation of complex multi-container microservice architectures without exceeding hardware limits. With VMM, local hardware functions as a fluid, on-demand resource pool rather than a set of rigid, pre-allocated partitions. These architectural improvements affect the workflow of entire engineering teams. A common friction point in development is when containers behave differently across Windows, Mac OS, and Linux. Standardizing the virtualization layer via Docker VMM ensures consistent performance metrics across these different host operating systems. Because Docker VMM is currently in beta, users may still encounter some platform-specific compatibility issues. Docker is currently refining these beta limitations through iterative updates and releases. This standardized environment also supports the growing demand for local AI agent development. It is important to note that Docker VMM does not increase AI compute speed or raw GPU processing power. Instead, it provides the isolated and resource-efficient foundation required to test complex AI workflows locally without system instability. As workloads become more resource-intensive, a consistent virtualization layer is a necessary asset for reliable development. Docker's move to control the lowest levels of its runtime environment signals a shift in its long-term strategy. Docker Desktop 4.87 demonstrates that optimizing local development requires direct ownership of the underlying infrastructure. The removal of third-party hypervisor overhead provides a toolkit optimized specifically for the developer's code. The result is a set of measurable gains: faster startup times, lower file I/O latency, and flexible memory scaling. This optimized local environment closely mirrors the efficiency of production cloud deployments, aiding cloud engineers in moving code from local machines to the server. The integration of VMM provides a vertically integrated environment that establishes a new technical baseline for modern container workflows.